Question number 4 is a nod to that practicality I was just mentioning at the end of the previous video, because financial institutions like banks obviously recognize that people want to get as much interest as they possibly can, but they also don't want to expend a whole bunch of their own energy and manpower to do it because they know that the payoff is very insignificant. So what mathematicians have done, and this is really in a tandem effort with both mathematicians and banking folks, is they've essentially generalized the process of compounding interest to a much simpler formula that banking calculators and computers can easily do without having to do all of the tediousness that you had to do when you did this calculation by minute. If you remember doing your own work here by minute in number 3, letter A, there was a lot here. I mean, first you had to figure out how many minutes were in a year. So you had to do like 365 days a year times 12 hours a day, or 24 hours a day times number of minutes in an hour, that sort of thing. It takes a while. Dimensional analysis or stoichiometry kind of comes in handy. That's a lot of work. Banks aren't going to do that amount of work for every individual customer, even on a computer. It's kind of crazy. So when we do this banking calculation, we have essentially generalized it all the way down to a much simpler, cleaner calculation that we call PERT. PERT is the same formula that you were doing. It's the same formula that we were using in the table for essential purposes, but it's obviously much shorter. Notice P is still principal, but it doesn't have the parentheses. It also has a slightly different exponent. Remember how the exponent in our table was n times t? Now it's r times t. You might be looking at that going, whoa, 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 what the heck? But when you actually dig deeper into the foundations of PERT and where PERT came from, PERT was the result of some very brilliant mathematicians who said, hey, wait a minute, let's dig a little bit deeper into what's going on here. Let's make sure that we really understand the math behind this calculation. And what they actually found is that the letter E, which stands for a specific number, actually did the entire bit of heavy lifting that this parentheses with the power of n was doing in our long complicated formula. So what's so interesting is when the mathematicians who delved into this really looked at it, they realized we could replace all of these characters, parentheses 1 plus parentheses 0.04 divided by 1 parentheses to the power of 1 times, with the letter E. They basically were like, whoa, 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 wait, hold on. Let's be simple about this. Now they had to make E stand for a number. That's why it says in this question number 4, E is a constant value. But E can be thought of kind of like pi. Remember how pi always stands for a number, 3.14? E stands for a number as well. It's 2.718, which is not important right now, and you don't need to know about that number right now. But what I want you to recognize is E is a number, and E is a number that specifically is stored in most calculators so that you don't actually have to memorize it or type it in yourself. Most calculators have a pi button. I'm using mine as an example. There's the pi. And E is usually right around the same. Yep, right here. There's E. So almost every calculator has an E button, or at least the option to access E. Check out whatever calculator you have and see if you can find the button that says E. Now, I'll admit, this packet was written as if you had a graphing calculator in front of you, and we were going to do these questions in class as if you had your own graphing calculator. We don't have that luxury now from home, so that's why we're going to have to kind of be flexible about this question. And if yours doesn't quite follow what mine is going to show you on the YouTube screen, feel free to just be flexible and adapt. Now it says using the values of this guy's investment in number 3 and the equation above, let's see what would happen if we use the banking equation, PERT, instead of the long complicated formula to say, all right, what if we just compound all the time? The thing about PERT that I should have mentioned before I started going off on this little tangent here, the thing about PERT is that PERT is meant for what we call continuous compounding. Remember how if you're compounding by minute or by second or by millisecond, it's hardly making a difference at that point. You're compounding so much that it's dividing your money into such teeny, teeny, tiny little payments that it's hardly like any payments actually making a difference anymore. We call it continuous compounding for that reason. You're basically just going to compound little bits all the time. Little tiny bits constantly, 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 all the freaking time. So, continuous compounding is a phrase that you're going to hear a lot. And continuous compounding is basically our way of saying, hey, yeah, use that PERT equation. If you see the phrase continuous compounding, we're going to use PERT. That's why in letter B, it says calculate the value of his account if it was compounded continuously. There's that word continuous again. That means use PERT. Now, to use PERT, it's pretty straightforward. P still stands for principal. So his principal investment in number 3 was initially $10,000. So I'm going to keep that. E is a constant, so I'm going to write E, and I'll show you what to do with it in a second. But for now, it's not a variable. It doesn't plug in as anything. Write the letter E. To the power of R, that was our rate as a decimal. That was 0.04 times T, which was our time he was investing for 10 years. So now, that is my PERT equation. If I type that into the calculator exactly the way I see it, it's going to look like this. 10,000 E to the power of, and I'll use parentheses anytime I have two things in the exponent spot, 0.04 times 10. And now, notice the results. $14,918.25, which happens to be the exact same amount that we calculated in the table. It's hard to see because of the glare, my apologies. The exact same amount that we calculated by minute. But notice the difference. In the table version of the question, I had to figure out how many minutes were in a year, and I had to do that whole freaking formula with all those parentheses. Took so long to type in, compared to PERT, which took me just a few seconds to type in. My calculator already knew what E was, and it's like I didn't even have to think about it, and I got the exact same answer. You can tell why banks like to use PERT. It's simple. They can program this in a banking computer and a calculator in a matter of seconds, where typing by minute, all of these extra characters, imagine all the coding involved for each individual customer, crazy amount of time for the exact same answer. Of course, banks are going to take the most practical approach. They're going to use PERT. So PERT is a fantastic equation because PERT gives you all of the same things that you need, but it basically works for when that value of n is so obnoxious that it's not even fun to calculate. So we won't use PERT for everything. PERT actually is really only for when we use continuous compounding. When we want to compound so often that we're going to do a ton of calculations. Tons and tons and tons and tons of them. The compound interest formula will still be valid for things like quarterly. That's only 4 calculations. We can do that. Monthly. That's only 12. We can do that. But continuous, that's like millions and millions and millions of calculations, that we're going to use PERT for. So, in general, hopefully you can see now that PERT, or continuous compounding, has a bit of an advantage that compared to doing tedious calculations in a table can seriously help us get to a calculation answer faster. Wrap your head around that for some time, and then in the next video we'll talk about number 5, where we can start to be a bit more practical about saying, okay, how do we do these problems fast?